Hello guys, this is Aim and welcome to the channel. In one of the last Tech Talk sessions, we have discussed about a 280-year-old algorithm which was used in Google Trips. As you may not know, the problem statement in that was very simple. How do you connect multiple places in order to reduce the cost? It was very similar to the problem of traveling salesman, but we have used an approximation algorithm to somehow reduce the time complexity. So if you haven't checked that out, I strongly recommend you to check that out, and you may get more insights about what I'm talking about today. The part of the solution of the algorithm used in Google Trips was creating a minimum spanning tree. A minimum spanning tree is a tree which spans across the graph, which contains edges and vertices. Mainly, the point to be noted is the graph is undirected. So we have to create a tree which spans across the graph and which connects all the nodes in a way that it connects in a less cost as possible. So that is the definition of minimum spanning tree. But how do we construct it? So there are two famous algorithms to construct a minimum spanning tree. One is Prim's and other is Kruskal's. In this video, we will be introduced to Prim's algorithm. In later, after a couple of videos, maybe we will be also dealing with Kruskal's. So in the Prim's algorithm, today we'll be understanding the basic nature of the Prim's algorithm, as well as getting a far less efficient algorithm, but we will get insights about Prim's algorithm instead. So in the upcoming video, we will also learn about efficient algorithm to solve a Prim's algorithm. So without any further ado, let's get right into it. So we are back at our whiteboard. So Prim's algorithm was invented by the scientist called Prim. So this is the example we are considering. So this is a graph G with vertices V and E. There are 5 number of vertices and the edges are 1, 2, 3, 4, 5, 6, 7. 7 edges. This is an undirected graph. So the key idea of the algorithm is to find all the adjacent edges of the candidate nodes and choose the light edge. So let's go deep into the algorithm and understand what are the candidate nodes and what is a light edge. So the Prim's algorithm has a global set called MST where it contains all the candidate nodes. So candidate nodes are the nodes which are to be analyzed. As we are constructing a tree, every tree has a root. So let's consider A as our root. So let's put it into our global set MST. So now A will be the part of our minimum spanning tree. So let's color it green to note that it is the part of minimum spanning tree. As we have discussed earlier, we need to consider all the adjacent edges of A now, of a candidate set. So candidate set is now has only one element, that is A. So let's consider all the adjacent edges of A. So we can go to B from A or A from D. So these are the possible adjacent edges. Now let's consider its weights as well. So the next step is to find the minimum edge which has the least cost. So it is very obvious that A to B is the least. Let's choose B as our next edge. We will put B in our global set as it has become the part of the minimum spanning tree. So we need to assign it as visited. So now we have to consider all the adjacent edges of the candidate set. Candidate set has now 3 elements. So all the possible edges are we need to ignore the edges, or we need to ignore the vertices which have been already added to the set. That means which are colored green here. So we will not consider A to B now, but we have to consider A to D, and we are done with A's edges, but we have B now. B have B to C B to D, and B and E. As this is an undirected graph, we have to consider each and every possible adjacent edges. So these are the possible adjacent edges of the candidate set. So let's consider its weights as well. 6, 3, 8, and B and E is 5. So now we have to find minimum of these. If we find minimum, we have 3. So now we have to consider this edge for our next span. So the vertex that is to be added is C. So let's add C to our global set MST, and let's color it as green because it is already added. Let's wipe out all these adjacent ones. Now our candidate set has 3 elements, A, B and C. Let's consider all the possible adjacent edges for the candidate set. So A and D, B and C is not added because it is already there in the minimum spanning tree. So B and D, B and E, we are done with B now. C has C and E, that's it. C and B is not considered because B is added to the set. So let's consider its weights. A and D is 6, B and BD is 8, BE is 5 and CE is 7. So the minimum of this is 5. So the next span will add E to our global set. So we will add E, and let's color E as it is already added. So this is how the spanning tree will be constructed. The last and only node we need that is yet to be spanned and added to the minimum spanning tree is D. So let's do that as well. So let's consider all the possible edges. AD, B, D, and C. C doesn't have anything left, and E has BD. So these are all leading to D. So let's consider its weights. A and D is 6, BD is 8 and ED is 9. The minimum is 6. Therefore we need to add D as part of the tree, A and D. So we need to add edge A and D, this one. So finally, let me represent the tree which we have constructed. So this is the tree which we have constructed using the Prim's algorithm. So as you can see, the weights are minimized and the total cost is 2 plus 3 plus 5 plus 6, that is 10 plus 6, that is 16. 16 is the total cost of creating this spanning tree. So why did I call this this particular algorithm to construct the minimum spanning tree as inefficient? So it is very obvious that we are considering every edge possible, so each and every node which is in the candidate set. This algorithm runs at the worst case at big of V square. V is the number of vertices in the graph.